Okay, so to this point we've proven the correctness of Prim's minimum spanning tree algorithm under an assumption that the cut property is true. So the purpose of this video is to supply the missing proof to convince you of this cut property. Let me remind you where we stand. So through all the minimum spanning tree videos, we're assuming distinct edge costs. All of this can be extended to edge costs with ties. In particular, there's a version of the cut property when edges have ties. But we're just going to focus on the main ideas which were exposed already with distinct edge costs. So what does the cut property say? Well, it's meant to be a guarantee that an edge is safe to include in your tree so far. So it justifies an iteration of a greedy algorithm like Prim's algorithm. Specifically, consider an edge of a graph, and suppose you can find some cut, a comma b, so that amongst all the edges that are crossing this cut, E is the cheapest. So the edge E has to not just cross this cut, but it has to be cheaper than any edge that crosses this cut. If you can find just one cut of this form, so that E is the cheapest crossing edge, then it's definitely not a mistake to include E in your tree. You definitely want it. It is in the MST. So this is a non-trivial claim, and let's turn to the proof. At a high level, the plan will be not that different than the correctness of our greedy scheduling algorithm for minimizing the weighted sum of completion times. That is, we're going to use an exchange argument embedded in a proof by contradiction. And the type of contradiction will be of the same form. We'll start with an optimal solution. Suppose it doesn't have the property that we want it to have, and then we do an exchange to make it even better, contradicting the assumption that this solution is optimal. So specifically, if we argue by contradiction, we assume that the cut property is false. So let's just make sure we understand what that means. If the cut property is false, then there's a graph, and there's an edge, which actually is the cheapest crossing some cut, and yet that edge does not belong to the minimum cost spanning tree T star. The plan then is to exchange this missing edge E with some edge that is in the tree T star, which is more expensive, thereby getting a better spanning tree providing the contradiction. So this idea currently is a little bit hand-wavy. To really execute it, we have to specify which edge we're going to exchange the edge E with. That's a subtle point, and we'll develop it over the next couple of slides. So let's begin with a sort of first cut attempt at an exchange argument. So what's the world look like? Well, we have some cut of a graph. So we have one blob of vertices A, and then the rest of the vertices are in this blob B. This is the cut for which edge E is the cheapest. And by our assumption in this proof by contradiction, this cheapest edge E does not belong to the minimum spanning tree T star. That said, I claim, while T star may not have this edge E that crosses this cut, it better possess some other edge crossing this cut AB. So why is that true? Well, suppose the opposite. Suppose, in fact, T star did not have any edge crossing this cut AB. Well, then T star wouldn't be connected. It wouldn't span all the vertices, right? Remember our proof of the empty cut lemma. So if you had this empty cut, then there's no way to have a path from one side to the other side. Okay, but that's spanning trees have to have paths between each pair of vertices. So T star as a spanning tree has to contain something from this cut. By assumption, it doesn't contain edge E, so it contains some other edge. Let's call it F. That crosses this cut. Now, of course, since E is the cheapest edge crossing this cut and F is some other edge crossing this cut, F is strictly more expensive than E. And at this point, we seem beautifully set up to execute the desired exchange argument. We have the edge that the optimal solution is missing. We have a candidate replacement, edge F, which is more expensive. So if we swap E and F, hopefully we get a new spanning tree that has strictly smaller cost, providing the desired contradiction. But things are more settled than they were with the scheduling application. The reason being is that schedules are simply sequences of jobs. So whenever you do an exchange of two jobs, it's clear you get another schedule. But spanning trees and graphs are subtle objects. And there's a question, if we take a spanning tree and we add one new edge and delete an edge, do we get another spanning tree of the graph or not? So the following quiz is going to ask you to think about that question carefully. Okay, so what we wish that the answer to this quiz was either answer A or answer C. So A would be the cleanest solution if it were always true that when you take a spanning tree, you take an edge outside of the spanning tree, and then you swap those two edges, you get a new spanning tree, then in fact our proof of the cut property would be done, right? We would just go on that previous slide, we would rip out the edge F from the spanning tree, we'd plug in the edge E, because E costs less than F, we'd get a spanning tree which was cheaper, and we'd be done. That would be our contradiction. Now if A wasn't true, we'd still be okay if C was true. If maybe not every swap yields a new spanning tree, but at least if you're swapping in the edge that's the cheapest crossing some cut, you get a spanning tree, then we'd also be golden, because in fact we only are trying to execute the swap, the exchange, using an edge which is the cheapest crossing some cut. If you go back to the previous slide, you'll see that was the only case we needed this fact to be true. Unfortunately, the correct answer to this quiz is D. You need not get a new spanning tree when you execute an exchange, even if you're plugging an edge which is the cheapest edge crossing some cut. So to understand this better, let me redraw the picture that we had on the previous slide. We had our cut AB, we had our cheapest edge E, which by assumption does not belong to the spanning tree T star, but we observed that T star has to contain at least one other edge crossing this cut because it's connected, and we called that F. And we're wondering if swapping E and F yields a new spanning tree or not. So to reason about this, let me just draw you what the rest of the spanning tree might look like. So in this picture, the spanning tree T star is given by the pink edges, and it's just this path of 5 edges on the 6 vertices. So what happens if we exchange E and F? Well, unfortunately, something bad happens. So we certainly get a new subgraph with 5 edges. After all, we just subtracted one and added one. But this new subgraph fails to be a spanning tree. It fails on both counts. First of all, it obviously has a cycle. It has a 4 cycle. And secondly, it's not connected. The upper right vertex is just totally disconnected from the rest of the vertices. So that's no good. That's an exchange which just does not produce a feasible solution, and it is not therefore useful in our proof by contradiction. Now, if we wanted to salvage some hope from this seemingly promising proof plan, we could take solace from the fact that there's not just one pink edge crossing the cut AB. F isn't the only one. There's actually this other one on the bottom. So let me call that E prime. Now, E being the cheapest edge crossing this cut overall, not only is E cheaper than F, it's cheaper than E prime also. So in some sense, with our motivation, we could care less which edge we exchange E from crossing this cut, because it's cheaper than all of them. And we see that at least in this example, swapping with E prime yields a good solution. It yields a feasible spanning tree. So what have we learned? What we've learned is that if we want to execute this exchange argument, we cannot blithely exchange with any edge of T star that crosses this cut. So the best case scenario, so what we're hoping is true, that we can always find some suitable edge, like E prime on the previous slide, so that when we execute this swap, we do in fact get a spanning tree. And I'm happy to report that we can indeed always do this. So what I need to explain is the procedure by which we exhibit this edge E prime, which doesn't get us into trouble when we swap, which still gives us a spanning tree after the swap. So let me explain the procedure by which we identify this magical edge E prime that we can swap with and still be a spanning tree. So here's the way to think about it. So we've got this spanning tree T star. We've got this edge, which is not yet in T star. Now, if we just plug E into T star, we're going to get a cycle. Why? Well, a spanning tree, remember, it has a path between each pair of vertices. So if this new edge, maybe its endpoints are U and V, T star already has a path between U and V, so when you plug in this new direct edge between U and V, it closes the loop. It gives you a cycle. So let's go ahead and call that cycle capital C. Let me also redraw the picture from the example on the previous slide so you can see what that cycle was in that special case. Now here's the pattern to notice about this cycle capital C, at least in this example, which is that the lousy edge, the edge F, for which when we swapped we didn't get a spanning tree, that's off of this cycle capital C. Whereas the good edge, the edge where we could do a swap and get a spanning tree, E prime, that's on this same cycle capital C. And that turns out to be true in general. So when you add the edge to the spanning tree and you get a new cycle, that cycle is what furnishes the candidates for swaps that will give you a new spanning tree. So the one lingering concern then, we have this cycle. All edges of the cycle are going to be good candidates for swapping. We just need to make sure that there is some edge that actually crosses this cut AB, like the edge E prime does in the picture. But here we're going to rely on a fact from a previous video, the double crossing lemma. Remember, the double crossing lemma says that if you have a cycle that crosses a cut at least once, then it has to cross it twice, right? So if you cross once, then it has to loop back around, and then looping back around, it's going to cross it a second time. So this cycle capital C, we know it crosses the cut AB once. That's because it includes the original cheapest edge across the cut E. So it's got to cross it a second time. There's got to be an E prime in the cycle crossing the cut, and that's going to allow us to do the swap and get a new, cheaper spanning tree, completing the contradiction. So just to spell things out in a little more detail, so what we do is we first say we use the double crossing lemma. So we have this purported minimum spanning tree T star. We have this cheap edge E not in it. We plug E into the spanning tree. We get the cycle. We call the cycle capital C. The cycle crosses the cut AB once through the edge E. It crosses it a second time by the double crossing lemma. We're going to call that edge E prime. Since E prime crosses the same cut as E, we know E prime is strictly more expensive than E. Remember, E is the cheapest one crossing this cut, AB. So now what we do is we execute the swap with this new edge E prime. So E prime's in T star. The cheapest edge E is not in T star, so we can swap them. We can rip E prime out, we can stick E in. Now something I want you to think through carefully at home, convince yourself this is true, is that because we plucked E prime from this cycle, this new tree, which I'm going to call capital T, this is a spanning tree, necessarily. You know, intuitively the reason being, you plug in E, you get this one cycle involving E, and then when you rip out E prime, you destroy the cycle. And because it's on a cycle, you don't destroy connectivity between any pair of vertices. There's still one path between each pair. But make sure you believe that, convince yourself at home. And once you're so convinced, you will also realize that we've finished the proof. We've executed our proof by contradiction. Since E was the cheapest edge crossing the cut, and E prime is another edge crossing the cut, E's got to be cheaper. Since T differs from T star only in the swap of these two edges, its aggregate cost has gone down, and that contradicts the purported optimality of T star, completing the proof of the cut property.